Good evening, everyone. And today we will be discussing the rest of the part for size reduction. Before starting today's session, I will wait few minutes more people to join for the live session today. Okay, so we can start today's session. Yeah. So let me introduce myself. I'm Smita. I'm PhD PMRF scholar in Department of Chemical Engineering, IT Madras. So here I am conducting this lecture as a part of my teaching assistantship of NPTEL and part of duty for PMRF fellowship. So in the last class we have discussed about the size reductions, equipments and other principles of crushing laws. So in this class we will discuss some rest of the size reduction equipments, basically fine grinding equipments as well as ultra fine grinding equipments. So in the last class it was remaining to discuss about the one part, that is crusher, which is impactors, or we also know it as a impact crusher. So you can see this is the typical picture for the impact crusher. So here is the rotor and here are the hammers are there, which uh, makes like impact forces, and it breaks down the larger feed particles into smaller feed particles, and the products will be collected at the bottom. So this is the example for single rotor, but when you are using the double rotor system for the same impact crusher, other mechanisms or arrangements will be same. Only instead of one rotor there will be presence of two rotors, and which will be rotating in the opposite direction. So let's start that impact crusher, which is also known as impactors, may be used as primary, secondary or tertiary crusher. They are the most suited for reducing the size of brittle and non-abrasive material. So coming to the impact crusher, it may consist of one or two rotors which is capable of rotating at a very high speed, that is 200 to 1500 rpm. It can rotate at a very high speed. These rotors are fitted with multiple impacting devices or hammers on the outer surfaces. Now, coming to the rotors and hammers, these are enclosed in a shell with breaker plates. So these are the breaker plates. Number 3 it has been denoted. So these are the breaker plates attached at a suitable location to aid in the crushing of coal or any material impacting on them. So here steel lined breaker plates are used or attached on the inside of the external shell. External shell is this one. So in the inside of the external shell, here are the breaker plates. And other appropriate locations they can be placed where impact force will be likely to happen. So some design may also incorporate fixed breaker screens at the bottom, fixed breaker screens, so that we can remove finer materials and we can also prevent their further size reduction. So due to very high rotational speed that we can maintain, impact crushers are vulnerable to trump iron or steel, and therefore they are always preceded by metal detector or magnetic separator. So here it is written that due to very high rotational speed, impact crusher sometimes it may uh, produce some iron and steel contamination from the lining inside the crusher. So always we are placing metal detector or magnetic separator for processing the product getting from impact crusher. That is safer use because we don't know the product, if it is somehow contaminated with some iron or steel particle, they may be they may cause a big risk in the downstream processes. So we always make sure that it doesn't contain unnecessary iron or steel particles. So we are placing metal detectors. The energy for breakage is imparted to the particle through the transference of kinetic energy from the rotor, which rotate at a constant speed and very high speed. So we are transferring the kinetic energy from the rotor to the particles. And as a result, the larger size particles, they may gain more kinetic energy than the smaller size particles, and hence there will be more shattering of the larger size particles. So one of the other thing that due to the absence of any product size control mechanism, in case of the impact crusher itself, there is always a good chance of oversized material that can easily pass through the crusher. So to maintain, the impact crusher is usually operated in a closed circuit to limit the top size of the crushed material. So now we are moving forward with grinders or fine grinders. Here we will discuss about hammer mill. So you can see the typical picture for a hammer mill, which is like hammering is occurring in this section, and through the small passage between these hammers, it may go through another round of attritions, and it produces reduced size of the particles. You can see from this picture or video, the larger size particles are gradually crushed down to ultrafine, not ultrafine but fine molecules. So this hammer mill is classified as fine grinder. So it can be used as a primary or secondary crusher for coal kind of material. Hammer mills are generally used for reducing size of the brittle and non-abrasive material in cases where the generation of the fines is of little or no concern. So we can easily use the hammer mill for those cases. Now hammer mills have a speedily rotating rotor. You can see this is rotating rotor, and where the hammers are attached at the outer surface of the rotor. So where hammers are attached at the outer surface of the rotor, here it produces impact force as well as attrition between the particles, and they more produce size reduced particles. A fixed grade plate is also attached round the hammer with a small clearance in the lower part of the machine. See this one, they are talking about this lower clearance fixed plate is talking about, through which the particles pass through. Size reduction in the hammer mill takes place through impact force as well as attrition between the interparticles. So incoming feed is impacted by the hammers and they shattered. Thus the fragments generated are directed to impact with liner or grit plate, resulting in further shattering. So the undersize of this, so whatever is passing through this undersize of the grit plate, which passes through the aperture present on the grit plate, it is collected and the oversized particles will be retained on the grit plate, and they are caught in the clearance between the hammer and the grit, and they are again taken away. See this part, they are again taken away. If they are not being crushed enough, they are again taken away, and it is again going for the next round of grinding. So the oversized particles are thus broken down by attrition occurring between the fast moving hammer and the grid plate, resulting in the generation of lot of fines sometimes. So this generation of fines is excessive in case of more fibril material if you are handling, for which grids with larger aperture may be used to reduce the fine generation. So for this grid size should be larger so that more of the particles cannot go this way, it can directly pass through. So we can avoid lot of fines generation. So we have discussed about the hammer mill. There is another type of hammer mill, that is reversible hammer mill. So here what is happening, to prevent uneven hammer wear and to increase the life of the hammer, reversible hammer mills are used, having rotors that can rotate on both sides. So here the rotor can rotate in both sides to prevent uneven hammer wear. By periodic reversible direction of the rotor movement, hammer wear can be kept at a more or less uniform level. Thus, it can optimize the performance and maintenance also and increase the lifetime. Due to high rotational speed, hammer mills are vulnerable to damp iron and steel. Therefore, for this case also it is always preferable to proceed with metal detector and magnetic separator. Feed moisture is very crucial in case of any kind of hammer mill. If the moisture content of the feed is very high, the residence time of the feed material inside the hammer mill will be more, and they may cause more fine generation and they will reduce the overall capacity of the hammer mill. So always we need to maintain the feed moisture content, and we can do that by using different kind of drying arrangements. So the next part we will be discussing about, that is fine grinder, that is rolling compressing mill. So a roller is typically a fine grinder that uses cylindrical rollers to crush, grind and pulverize materials through the forces which are compression force and shear forces. So here the material is being fed between two or more counter rotating rollers. They can rotate at different speeds where differential drive they can create to apply both compression and shear stresses. So the gap between the two rollers determine the final product size. The gap is narrow and precisely adjustable for grinding finer size material. They can they can even crush down to few millimeters to micron. So size reduction here occurs due to pressure, which is primary mechanism, and attrition between the two rolls, that is secondary mechanism. Here you can see this is the roller which is being rotating in such way, and here we are giving the feed from this. So here the grinding roller and grinding ring is there. So material will be here, and the material after pressure mm, uh, after the pressure acts started acting as a primary mechanism, they will pass through this opening, and they perform very fine grinding. But the advantage is that it this rolling compressing mill, they may produce uniform particle size distribution in the product, generates less heat and dust compared to the hammer mill. So it is an energy efficient process for medium hard material, and also gentle grinding preserves product quality. So the grinders generally reduce the crushed feed to powders, or you can say fine grinding particles. The product from the intermediate grinder might pass 40 mesh screen, whereas most of the product from a fine grinder would pass through 200 screen with 74 micron opening. The rollers in the rolling compressing mill will rotate on the stationary axis, which may be vertical or horizontal. So next we will discuss about attrition mill. So next we'll be discussing attrition mill. Here you can see that this is the feed for attrition mill. This one is the rotating disc. This one is the casing for operation. And here is the discharge of the particles. And these are some stationary plates or disc. So here the particles of soft solids are wrapped between the grooved plate flat surfaces of the rotating disc. Feed enters through an opening in the hub of one of the discs and passes outward through a narrow gap between the discs. The width of the gap within limit can be adjustable. At least one of the discs is spring mounted to allow unbreakable material. Discs with different patterns such as grooves or corrugations or tooth kind of pattern, they can perform variety of operations like grinding, cracking, granulating or shredding. So here a single runner attrition mill, they contains disc of rock emery for reducing solids like clay material, talc powder. Metal discs are also used for crushing hard material like wood or starch or insecticide powder or wax. So metal discs are usually made up of white iron and stainless steel for any kind of handling of corrosive material. Here the double runner mill also give fine products but processed soft solids only. Air is drawn through the disc to remove the product and prevent any kind of choking in the operation. More heat is generated, which can be removed by spraying water or refrigerated brine. So here the removal of heat, it is very essential when you are dealing with very sensitive material like rubber or other kind of thing. So here we have discussed that single discs and double discs two kind of arrangement can be possible in attrition mill. So here we are comparing the two different design where the disc diameter is almost same for two cases but the speed is more for double disc runner. Capacity is almost same, product size can be also same and power consumption is also same. Okay, so next thing we are going to discuss about tumbling mill, which is very important for this course because under this tumbling mill we are going to discuss about ball mill. So tumbling mill always have a cylindrical shell slowly turning about its horizontal axis and filled with half of the volume with some grinding media. Around 30 to 50% it is used. The shell is usually still lined with carbon steel plate or porcelain or silica rock or rubber. The grinding medium can be metal rods in the rod mill, metal balls in the ball mill, or flint or pebbles or zircon sphere in the feeble mill. So, depending on the and different form of the grinding medium, that those are the different names for the grinders. So in all kind of tumbling mills, the grinding element carried up the side of the shell. From there, they fall on the particles underneath. So the energy expended in lifting the grinding elements is utilized in reducing the particle size. Therefore, breaking pattern in the ball mill is always impact force alone. Whereas in other tumbling mills such as rod mill or other feeble mill, the particles are reduced from the rolling compression as well as attrition. The grinding reed or grinding rods are usually steel made and 25 to 125 millimeter in size, and they are extended the full length of the shell. So these rod mills are intermediate grinder, reducing 20 feet size to 10 mesh screen size uh, products. So you can see in kind of this is the general picture for a tumbling mill. So it rotates in this way. So here ball mill and rod mill, the main difference is the grinding medium. Here the balls are the grinding medium and here the steel rods at different L into L is to D ratio they are introducing. So this kind of action of ball, these zones we are going to discuss in few coming slides. So now we are focusing on the part tumbling mill is ball mill we are going to discuss. So as we know that grinding medium, which are metallic balls in the ball mill, they occupies around 30 to 50 volume percent of the cell. Now the diameter of the balls that are introduced as a grinding medium that can be 2 to 15 centimeter depending upon the type of the material you are going to grind, and also the diameter of the shell. So here the shell diameter and length, the relationship is L is to D ratio is 1 to 2 is to 1. It can be 1 is to 1 or it can be 2 is to 1. It is generally used for the last stage of comminution for very fine grinding. So now I am going to discuss about patterns of motion of the balls inside the ball mill. There are basically three regime it follows when the grinding is happening through inside the ball mill. So the first step when it is at a very low speed or slow speed in the ball mill, the milling balls are taken along by the shell rotating is taken away. It is taken along with the rotating shell and unroll upon each other, and there is kind of attrition occurring. So by the force of attrition only the grinding is happening. It is known as cascading regime. The second part, when you are slowly increasing the speed of the ball mill, it follows the cataracting regime where the balls detach from the rotating shell and they fall down due to gravity. And when they fall down, they create impact force. So in this cataracting regime, we are having two kind of forces. One is impact force, mostly occurring in the cataracting regime. They are um, they act with high intensity on the bulk or on the opposite wall. So while repeating free falling back of the grinding medium happens due to gravitational force. And the last stage is centrifuging or rolling regime, where when you increase the speed of the ball mill more higher, there will be higher speed of the ball mill or very high speed. It turns out to be centrifuging, where in this regime the ball align completely with the rotation of the shell and it doesn't even interact with there is no attrition force because they don't interact each other, and there is no impact force as well. So in this centrifuging or rolling regime, no grinding is occurring. So now we are going to discuss about the critical speed of the ball mill. So just now we have discussed about the point where we have discussed the maximum centrifugation is occurring. Suppose this is your shell, ball mill shell, and one ball is at like it is having this is the ball at the stage of centrifugation. This is your ball. So in that part, you are this is the radius of the ball is r. So if you draw a circle, so this one will be capital R minus small r, because capital R is this, while capital R is radius of the shell and the small r is radius of the ball. So we are now going to um, case at the onset of centrifugation. We can have gravitational force equals to centrifugal force. Gravitational force m into g, centrifugal force mv square by capital R minus small r. From where we are getting g equals to v square by capital R minus small r. We also know that it is rotating, so v can be written as r minus small r into omega, which is into 2 pi nc. nc is the frequency or speed. So here we can write v square 4 pi square nc square. So we need to know what is nc. nc is critical speed, which is an rps. So nc can be written from here g by nc square can be written into 4 pi square. From there we can write nc equals to 1 by 2 pi root over of g by capital R minus small r. So this is the formula for calculating critical speed of ball mill. So we have now calculated the formula for critical speed of ball mill. So let's now do a numerical to understand that how to imply this equation. So the equation says a ball mill of 1.8 diameter is loaded with steel balls having of the diameter of those steel balls is 6 cm. Now the rotational speed of the ball is kept 75% of the critical speed. So what is the operational speed of the ball mill, and you have to calculate in RPM. So for your information, you already know critical speed equals to 1 by 2 pi root over of g by capital R minus small r. Now you put all the values. Okay, capital R is 1.8 divided by 2.9 meter. Small r is Small r is 6 centimeter. So we can calculate It is coming in RPS. So we have to calculate in RPM. So now critical speed is that's what we have calculated. Now uh, we need to know what is the operational speed, that is 75% of the NC, which is coming around 24.45 RPM. So this is the way we are utilizing that equation for calculating critical speed. So in the next part, we are going to learn about ultrafine grinders. So in the ultrafine grinders, this one is the fluid energy mill. Very interesting to know that ultrafine grinding can be done based on dry basis, or it can also be done on wet basis. So in the fluid energy mill, we generally do wet basis ultrafine grinding, and using the hammer mill with internal classification, we do dry basis. So in fluid energy mill, the particles are suspended with high uh, velocity gas stream or superheated steam. The gas is injected along the particles in the confined cylindrical chamber. Some reduction occurs when the particles strike and rub against the walls of the grinding chamber, but mostly the particles reduction happening due to interparticle attrition force and impact force due to high turbulent flow, because we are introducing very high velocity gas stream. Now the suspending gas is usually the compressed air or superheated steam. Generally we introduce at pressure of around 7 atmosphere through the energizing nozzles. These are the nozzles. So the high speed, high velocity air or gas is introduced in the confined chamber. Internal classification keeps the larger particle in the chamber until their size reduction is happening according our design. And the classification of the grounded particles takes place at the upper bend of the chamber in this region. So as the gas flows with high speed around this bend, the coarser particle will be thrown outwards and it will be collected again, circulated again, whereas the fine particles will congregate inner walls of the chamber and they will be collected from this. So here that was the classifier outlet, because the fine particle will be collected, but the heavier and bigger particle will be again circulated back in the confined chamber. So a discharge opening at the inner wall is connected to the cyclone separator or back filter for the product classification. Feed size is 12 mm, but it is more effective when the feed size will be less than 100 mesh screen. Generally, product size is 500 nanometer to 10 microns. So the amount of steam that are used 1 to 4 kg per kg of the product we are targeting, and compressed air will be used around 6 to 9 kg of air per kg of product it is used. The capacity of fluid energy mill is around 6000 kg per hour. I hope this picture and the description is uh, clear to all of you. The next one we are going to discuss about, that is agitated mill. So here you can see the picture that it is effective for very ultra fine grinding, and particle size of the product can be 1 micron or in further fine size. Here we introduce concentrated slurry and into the agitated mill from the top, and the product is withdrawn from the bottom. Also there will be one screen so that it can screen sizing can be done. It consists of the grinding medium that can be ball, pellet or sand grains. They are is dispersed in some fluid. The main force here by which the fine grinding occurs, that is also impact and attrition. In order to reduce the size of a very hard and abrasive particle, feed particle, we are using multi-armed rotor or impeller device that can be used to provide very good turbulence inside the reactor. The capacity of the agitated mill, they may vary from 4 to 1200 liters. The next and the last one we are going to discuss, that is classifying hammer mill, which is the similar process but we are using dry grinding. Here a set of the hammers that is held between the rotor and the valve, such as conventional hammer mill we operate. In addition to the hammers, the rotor shaft carries two fans, which is very important for this case because they are used to draw the air from the throughout the mill. On the rotor discs, a short radial vanes are placed to separate the oversized particles from the acceptable size. So in the grinding zone, solid particles are given with high rotational velocity. Thus, the coarser particles are concentrated along the wall due to centrifugal force acting on them. The air stream carries the fine particles from the grinding zone to the direction of AB. So there is separate veins and the fines are collected from here. The oversized particle will be thrown down in the downward direction of BA. So the passage of particles through the veins is depend on the two predominal forces, which is centrifugal force by veins and drag force by air stream. So here the coarser particles are thrown back into grinding zone by the veins and fine particles are carried by the air stream. Average product size will be maintained here 1 to 20 microns. Capacity of this dry grinding hammer mill is 1 to 2 tons per hour and power consumption is also 40 kilowatt hour. So as a first part of this today's lecture of week 4, we have just now completed the part for size reduction equipments along with some remaining part for the crusher, fine grinding and ultra fine grinding. So I will take few minutes break so that I can present you the next part for today's session, which is solid storage and conveying.